Welcome back, folks. In our first half of this module, you got a good look at the way that metals and nonmetals bond to each other. And in that type of bonding, you have this transfer of electrons from an atom that generally doesn't want to have its last few valence electrons to something that's looking to pick up a few extra ones. But something you saw at the end of our Zoom meeting on Wednesday was that there are compounds out there that don't involve metals at all, that exclusively involve nonmetals. And the problem with our current model is that it doesn't account for bonding between two atoms that both need more electrons. Let's head to the whiteboard. As we said, if I have a metal atom and a nonmetal atom, this model of transferring electrons from one to the other works out great to explain the way that we end up with compounds. We turn this into a stable cation, that into a stable anion. They attract each other, causing the formation of an ionic bond, and you wind up with a compound. On the other hand, if I make this also a nonmetal, odds are pretty good this is not going to want to part with its electrons. For example, a compound like nitrous oxide or laughing gas made of nitrogen and oxygen is not going to form in quite this same way because this is not going to part with any electrons. I might look at this and say that the nitrogens each need 3 more and that the oxygen needs 2 more. But there's nothing around here that will actually provide the new electrons. So we need a little bit different of a model. If all atoms are pulling electrons towards them, the best I'm going to be able to do is sharing. And so that's instead what we're going to do. When nonmetals bond to each other, they share their electrons with each other. And so when you're sharing electrons, we have a word for this. If you think about sharing workload or sharing objects, we generally use co as a prefix for that. And so this type of bonding, where we share outer electron shells and outer electrons period, is referred to as covalent. So same root word as valence electrons, but we're doing it together. So covalent bonding is what we get out of this. And covalent bonding has a really interesting way of coming about that is all about these same forces we've been discussing as we've talked about energy. So if I have a pair of hydrogen atoms, let's start nice and simple with the simplest atoms we have. Each one is going to consist of a proton and an electron. And I'm going to do a little color coding on the opposite side here and make this one a blue nucleus and a red electron. If I have these two atoms very, very far apart from each other, the dominant force that's going to be felt by this nucleus is attraction to that electron. And the dominant force this electron feels will be attraction to its nucleus. These two are going to impart some force. It's going to be weaker because they're further away. But the other thing is, if they really are very distant from each other, those two forces are going to be practically of identical strengths and pointing in exactly opposite directions. So for example, this electron is going to feel repelled by that electron, whereas this nucleus is going to feel attracted to it. But this electron is going to feel attracted to that nucleus, while this nucleus feels repelled by it. And so notice if I sum up the forces here, both of these forces are going to cancel each other out, and so this atom basically doesn't feel the presence of that when it's very far away. On the other hand, when I let them approach each other, let's go ahead and redraw them here, but much closer to each other. Okay, so there are my atoms. Now they've gotten a lot closer together than they were beforehand. And this time around, the forces are all going to be of approximately the same strength because the distances are all really similar. Now if I think about this nucleus, it's got the attraction. I'm going to just focus on the nucleus for now. It's got that attraction to its own electron. It's got as well a pretty strong attraction to that electron and a repulsion from that nucleus. All roughly the same strength. But the big thing to notice now is as they get close enough, you can kind of resolve the attraction to this electron and the repulsion from that nucleus. They're not in exactly opposite directions anymore because you're close enough now that they're able to be pointing in slightly different directions because these aren't in exactly the same spot. Now the same thing is happening all over this group of 4 particles. This electron is feeling attraction to the nucleus, but repulsion from that electron. This electron is feeling attraction to nucleus, repulsion from that electron. And this nucleus over here is feeling attraction to electron, repulsion from nucleus. If we allow these things to move around, to find a spot where you maximize the attractions and minimize all the repulsions, what you eventually end up with, pretty much without fail, is this. And this arrangement is going to allow the electrons to feel mutual attraction to both nuclei, but it's going to keep this repulsion between the electrons and between the nuclei at bay enough that it can stay in this general arrangement. And what's wild about this is that now, if I pull this nucleus away, it's going to drag the electrons with it, which will subsequently drag this nucleus towards it. And if I push this nucleus to the right, that is going to push this nucleus away a little bit, and the electrons will restabilize. And so what we have here is a very stable arrangement. In fact, what we've just built is our first model of a molecule. And this whole thing is going to operate as one unit now. I want to point out one other big thing, because we're going to learn how to build models of molecules for much bigger atoms with a lot more electrons involved. Notice that now that I've drawn it this way, you don't know which of these electrons is this one versus that one. You have no idea which one it came from, and in fact, for all you know, I spun the whole thing around, and this is that nucleus, and this is that nucleus. You'd have no way of telling at this point. And I want you to bear that in mind. When we build models, the electrons at the end of this belong to the whole molecule. We don't tend to think about them belonging to an individual atom anymore if they're involved specifically in the bond. In order to map out the way that electrons are shared in covalent bonds, we write what we call Lewis structures. And those structures involve representing the nucleus of each atom with its atomic symbol, and then putting in dots to represent the electrons involved in bonding. And so for what we just drew, you would write the 2 nuclei as a pair of H's and then put 2 dots in between to represent the 2 electrons. Now for hydrogen, those are the only 2 electrons we have. For bigger atoms, we're going to have more electrons than we really know what to do with. And as we've seen, most of them aren't going to be involved in the formation of chemical bonds. So the key point here is that not only are we going to represent the nuclei like this, but the dots are specifically going to be valence electrons, not just any old E's. And what we're going to do is start off by writing a few Lewis dot diagrams for these particular atoms without them being bound to anything. So take a moment, I'll do phosphorus for you very quickly. If we look at phosphorus, it's in group 5A, so remember that means it should have 5 valence electrons. Now because electrons repel one another, we tend to write them on isolated things by going around first, putting the first 4 in, 1 per side, and then the last one there. And so that would be my 5 dots all the way around a phosphorus atom. Try the same thing with magnesium, xenon, and bromine. Look them up in the periodic table, determine how many valence electrons they should have, and draw your symbol. After taking this moment, I hope what you've got is something like this. Magnesium should have 2 valence electrons. We'll put them on either side. Xenon is a noble gas. It's in group 8A, so it has 8 valence electrons. And so no matter how I do this as I go around, I'm going to wind up with 2 on every side. That's how we generally would draw xenon. Bromine, on the other hand, 7 valence electrons in group 7. And so, again, we're going to wind up with this. And this is the same result I would have gotten from putting 1 on each side to begin with and then continuing onward. I'm only going to have this one little spot. When you come back for the next video, what we're going to start doing is building molecules. And I'm going to teach you a method that's a little bit different from the one in your book that I think is better at keeping you from reaching a moment of paralysis that a lot of students run into. Tune in.